So, let us recapitulate some of the key features of superconductivity. We have seen that the resistivity So, the resistivity goes as this is as a function of temperature, and it suddenly goes to 0 within a very narrow energy or narrow temperature range at a temperature which is called as a superconducting transition temperature. So, just by itself it talks about a phase transition, but one does not know whether it is a superconducting phase transition even though the resistivity is going to 0, but there has to be some other tests for a superconducting transition, and one of them is the Meissner effect. So, basically it is a expulsion of the magnetic field. So, now this experiment is clear to most of you that how resistivity measurements are done. So, it is done in the lab with the help of a 4 probe measurement, where you actually pass current through 2 probes and measure the voltage across the transverse probes. So, this is how the current, or rather the current versus voltage characteristics, and from there the resistance, and resistivity is of course a quantity which is independent of the material properties, and it is independent of the geometric properties of the body or the dimensions of the body, whereas resistance is a quantity which depends upon, resistivity depends only on the internal, or rather the properties of the sample, whereas resistance depends also on geometric quantities. So, how is this expulsion of magnetic field seen? So, basically if you have a superconductor like this, and you put iron filings here, so basically scattered all over the place. So, this is the superconductor, and these iron filings which are like nails. So, if these nails are scattered all over and then you apply a magnetic field, so the magnetic field will not penetrate into the sample, but rather will go around it, and which will make these iron filings nicely lined up around the superconducting specimen. Okay. So, they will be nice, sort of nicely arranged around the specimen, and this shows that the magnetic flux density is actually concentrated around the specimen, and that is why they have lined up. All right, but that is an experiment which is dependent on getting those iron filings and doing this. Rather, there is a better experiment which talks about calculation of the susceptibility, and the susceptibility is defined as basically it is defined as dm dh in the limit h tending to 0, which means it is the slope of the m versus h curve, and this from a value nearly equal to 0, it goes to a value which is negative and maybe close to 1, because superconductor is a perfect diamagnet. So, chi is equal to -1 because m is in opposite in direction to h, and that is why it is it goes to -1. So, that is the susceptibility data is another becoming negative is another test for a superconducting transition. Now, there is another test which one often talks about, which is called as the discontinuity in the specific heat. So, specific heat shows a discontinuity across the transition. So, at T equal to Tc, there is a discontinuity, and one gets a sudden drop at transition temperature, and so this is so this drop can be calculated, and this drop can be sort of taken as a signature for a superconducting transition. So far what we have done is that we have seen that a superconductor is characterized by an energy gap which occurs, or which appears due to the fact that these Cooper pairs, they form a bound pair, and there is certain amount of energy that is required to break the bound pair, and that energy can be supplied in the form of magnetic energy, or it can be supplied in the form of thermal energy. So, we usually talk about both depending on situations that we are interested in, and we are going to talk about this discontinuity in specific heat. But before that, let us have a look at what does BCS theory give about the temperature dependence of this gap, that gap, energy gap that we are talking about, which arises due to the formation of Cooper pairs. So, let us talk about determination of Tc, which can be is also an important quantity. The transition temperature. Okay. So, what happens across the transition from a superconductor to a normal metal? A normal metal means that, just the way you know about from your first course in solid state physics, it contains a large number of electrons, and they can be pretty much described by the Sommerfeld model, which is a free electron model, and most of the properties such as conductivity, such as specific heat, etc., can be described by a non-interacting model or non-interacting physics. So, we want to know that what is the temperature at which a superconductor makes a transition to a metal, or in the other way, when the temperature is being lowered when a normal metal becomes a superconductor, and at what temperature does it happen, and that temperature is what we call as a Tc, or the transition temperature. So, just to remind you that we have computed the quasi-particle energies, which are given by this xi k square plus lambda square. Lambda is a function of t, where xi k is nothing but epsilon k minus mu, because we decided to work on the grand canonical ensemble. So, a chemical potential is needed to be introduced, and so these are the basically the single particle energies, or the band energies, and this delta is the gap. Now, at t equal to Tc, so delta goes to 0, and what happens is that your Ek becomes psi k with a modulus sign. Okay. So, this is the, so that happens to the quasi-particle energies, which boil down to the single particle energies, which should happen in a normal state. So, recall the gap equation. The gap equation was simply equal to 1 over V, it is a half, and sum over k, tan hyperbolic beta Ek over 2 divided by Ek. And so, this is the gap equation. So, what is V? V is the attractive electron-electron interaction, which we have seen that it appears because of interaction of electrons via phonons, and so that is the attractive part of it. And then we are summing over this, it is a k sum, it is a momentum sum that is done over this tan hyperbolic beta Ek by 2 divided by Ek, where Ek is the just what is written above, that is the quasi-particle energies. All right. So, then we need to compute this in order to compute Tc or delta, which is a function of the gap, and so this is equal to half. So, that is equal to this, and then you have a tan hyperbolic and a beta xi k by 2 divided by xi k, and so this is now we have to compute this, and in order to compute this we can convert the sum into an integral, and this integral if you need to do that, as has been told earlier, or you may be exposed to that idea from statistical mechanics or from your earlier solid state physics course, that in order to convert this into an integral, we need a density of states. Now, which density of states? Density of states is a function of energy. So, we should in principle include this into an integral and integrate over all I mean the density of states over the entire energy range that we are talking about. but then we know that superconductivity is a phenomenon that is taking place at the Fermi level or at the Fermi surface or at the Fermi energy. So, if we replace the entire density of states n epsilon just by n epsilon f, that should be good enough for doing this problem. So, we will let us just do that, and that yields this is equal to n epsilon f, and a little bit of care is needed in order to set the limit. The limit is basically set by the phonon energies which are given by h cross omega d, where we have simply written this whole thing as x and divided by x, and this is a dx. So, basically the x is taken as where x is equal to beta xi k by 2 and so on. So, you can just check that if you do that, then of course, your integral energy integral goes from the 0 to h cross omega d, if that is for the energy integral. But then since you have done a variable transform with beta etcetera coming, so that will be so the x c is equal to nothing but a beta c h cross omega d by 2. So, now this integral has to be evaluated in, if we want to know what is the transition temperature, and that can be evaluated, or rather that is a standard integral, and this integral has a value, let us call that as I, and this I has a value which is equal to, so this is A and a beta c h cross omega d. This is a standard integral where A is nothing but 2 e to the power gamma by pi, and which has a value which is 1.13. Okay. So, the whole thing now looks very simple. We are not going into the details of how to compute the integral, just know that this is a standard integral and can be computed either you compute it numerically, but this has a standard form in terms of which are called as the Euler's constant. This gamma is called as the Euler constant. Which has a value 0.577. Okay. So, too much of information is given already, but what is important here is that our beta c, or which we can write it as KTC. So, one can actually calculate the from, I just simplify this in order to get the KTC, which is nothing but equal to 1 over beta c. That comes out to be 1.13 h cross omega d and exponential minus 1 over n epsilon f v. Okay. This has several implications, as has already been told, that one this form of TC suggests that it is a non-perturbative theory. So, basically in terms of the electron-electron interaction. So, even if V is infinitesimal, so which means that there is an infinitesimal attraction between the electrons which can form a Cooper pair. However, this whole theory or this expression of TC that you are seeing is it goes as an exponential minus 1 by n epsilon f v, and for weak coupling superconductors n epsilon f v is much smaller than 1, or at least much smaller than 1, and in the BCS case it is taken as 0.3, well, which is smaller than 1, but not much smaller than 1. So, this tells you that delta at 0. Now, we also have, if you remember that we also have a form for the delta at 0, which is basically the magnitude of the binding energy of 2 fermions or 2 electrons measured from the Fermi surface, the individual Fermi surfaces, which also has a form which is very similar to that. If you please go back and check that, and that is with this really tells you that this is equal to 2 divided by 1.13, which is almost equal to 1.764. So, which means that delta, which is the gap at t equal to 0, is really of the order of Tc. It is slightly higher than Tc, it is 1.76 times higher than Tc. And in fact, this is a signature of BCS theory, that that is a 2 delta 0, which is about 3.52 kTc. In fact, for most of the superconductors, this value is between 3 to 4.5 kTc. So, that is the transition temperature, that is how the transition temperature is defined with regard to the value of the gap. So, the transition temperature of a conventional BCS superconductor is twice the gap divided by 3.52, and then the scale is Kb, which is the Boltzmann constant. So, so this is for most conventional superconductors. All right. So, this is what one really needs for knowing the Tc, because that is a very important quantity in the context of superconductivity. Now, let us look at that what is the form of the gap or the temperature dependence of the gap. Now, this we cannot compute analytically, but we have to do it numerically. So, just to remind you of this expression that we have just derived, this is equal to, this is a h cross omega d and a tan hyperbolic, and I am now writing it in terms of, so it is a beta xi square plus delta square. This is the full gap, and this is to the power half and divided by xi square plus delta square. This is to the power half, and then d xi, and this has to be computed numerically in order to get delta as a function of t. So, in the vicinity of t equal to 0, so what happens is that the temperature variation is very small, it is exponentially small, which is in the regime t going to 0, this gap is exponentially small, or rather this temperature variation is exponentially small, and it goes as exponential delta over kT, and which almost equal to 0. So, basically the variation is the temperature variation is 0, and where basically this tan hyperbolic term is very insensitive to the temperature variation and stays close to 1. Okay. And then I mean basically delta remains a constant, and so basically until so now you keep increasing the temperature until a sort of time comes when there are a significant number of quasi-particles that are excited, and in which case the gap starts going down. Okay. And as I said that I cannot do it without computing it numerically. So, one can compute it numerically, and one can find that the delta t is equal to a delta at t equal to 0. So, we will call it just delta 0, and there is a factor 1.74 as we have simply seen just earlier, and this is equal to 1 minus t over T c whole to the power half. Or we can simply drop this. Let me write this a little more neatly. So, this is 1.74 delta 0, and so this is the temperature dependence of the gap. Okay. And as I said that it can be computed numerically and plotted, and from the plot one can actually get this nice variation. So, this is as a function of T over T c, and this is delta T over delta 0, and this value is equal to 1 and this value is equal to 1. What I said earlier is that at very small temperature, much smaller than T c, the variation is extremely small and delta remains nearly a constant equal to 1, and then as temperature increases, the x axis increases, then there are sufficient number of quasi-particles that are excited and the gap starts going down, and at T equal to T c the gap goes down very sharply. So, that is the temperature dependence of the gap. So, these are all needed in order for us to understand that how these the specific discontinuity can be computed. So, before we go on to computing the discontinuity of specific heat from the BCS theory, from the results of the BCS theory, let us look at the thermodynamics. So, we will still call it a discontinuity of specific heat and so this is thermodynamic considerations. Okay. So, we write down the Gibbs free energy per unit volume as G equal to U minus T s minus H m, where we have neglected the PV term. So, that is the Gibbs free energy per unit volume, and if you want, call this as equation 1. Now, this is so from second law of thermodynamics, we know that du equal to TdS plus HdM. Again, we have not taken into the PV term, and that is the expression for the change in internal energy. So, if you put this, if you take a differential of 1 and put 2 into 1, then what happens is that your dg becomes equal to minus sdt minus mdh. So, just to show you the skipped step, we have a dg which is equal to du minus TdS minus SDT minus HdM minus MdH. And since Tu equal to TdS and HdM, so they cancel, giving rise to minus sorry, I had cancelled the wrong one, SDT, and you have HdM, so that cancels and gives me a minus SDT minus MdH. So, that is equal to equation 3. Let me just, so this is, you can keep it saying that this is equal to equation 3. Now, what happens is that M equal to minus H for a perfect diamagnet, which is a superconductor. Or a superconductor. So, that gives me dg equal to minus SDT and plus HdH, and then if I integrate this, I will get a G. Now, I write an S for the superconducting. So, this Gs, it is equal to Gs 0, Gs this is at H equal to 0 and plus H square by 2. Okay. So, this is say equation 4, and let me use a different color, and to say that this is Gibbs free energy for superconductor. Okay. Then of course, we want to compute the Gibbs free energy for the normal state, and so basically along a critical curve where the superconducting and the normal states are same. So, that is equal to a G n which is equal to a G s 0 plus a H c square by 2. So, G n, so this is G s and G n is Gibbs free energy. Okay. Now, this could have been G n 0, but G n 0 and G h 0 are same, because at s equal to 0, then they are same. And now, from equation 3, one can get a del G del T at a fixed h is nothing but equal to minus s. So, at equilibrium, Sn minus Ss, which is nothing but minus Hc and a dHc dt. Okay. So, what I did was that I took a derivative of this equation number, let us call it equation number 5, and have calculated 4 and 5 and have calculated this quantity. So, Sn minus Ss, which is equal to minus Hc. Hc is the critical magnetic field at which superconductivity is destroyed, and dHc dt, of course, this Hc is a function of T temperature, and so there is a slope of this Hc as a function of T comes, and of course, your Ss is the entropy of a superconductor. I will just write it in short for superconductor as Sc in 0 field. Okay. Now, it is very important to understand that let us call this, give this some name. What was the number earlier? So, this was 5, and let us give it as 6 and then give it as 7. dHc dt is always negative, because Hc goes down as T is increased. The critical magnetic field, the value of the critical magnetic field goes down as the temperature is increased. So, dHc dt is always negative. Which means the right hand side of equation number 7 is always positive, which means that the entropy for the normal state is always greater than the entropy for the superconducting state. And that makes sense, because the superconducting state is an ordered one, whereas the normal state is a disorder, and disorder always has larger entropy. Now, to calculate the jump in specific heat, which is defined as Cs minus Cn, where S and N of course stands for the superconducting and the normal regimes, which is equal to T, and there is a ddt of Ss minus Sn, and this is nothing but equal to it is a THc. Now, I will take a ddt of this equation 7. So, taking a derivative of 7, so this is equal to 2 d2 Hc dt2 plus a T dHc dt square. Now, it is important to understand that there are of course two terms there. but the first term is equal to 0 because at t equal to Tc, Hc equal to 0. So, the first term vanishes, but the second term continues to be there and which is equal to dHc dt. There is one square. So, there is one thing that you should not forget is that even if at t equal to Tc, Hc equal to 0, but dHc dt exists, which means the slope of the critical magnetic field with temperature that continues to exist, which gives rise to a discontinuity there. So, that tells that, so this is the formula for the specific heat discontinuity. So, if you know H c as a function of T, that how it varies. In fact, incidentally, for most of the superconductors, this Hc as a function of T that varies as just the way we have seen. So, it is Hc of T is Hc of 0 1 minus T by Tc whole to the power half. If you use this and calculate, you will get pretty much very neat value for the specific heat. Now, these are empirical formulas that are not believed very well or beyond doubt, but however, this for most of the conventional superconductors they seem to be following this behavior with respect to temperature. So, so let us call this as equation 8. So, from 7 it can be seen that at t equal to Tc, since Hc equal to 0, so Sn minus Ss is equal to 0. So, at the transition that is t equal to Tc, Sn is equal to Ss, which means that there is no latent heat. So, the latent heat of transition is equal to 0. So, which means delta S is equal to 0. So, this almost without any doubt establishes that the transition is a second order. However, of course, away from Tc, if there is a transition that could be first order. So, we have obtained form for the specific heat discontinuity and see that what the value is. So, you can of course calculate from here a dHc dt, take a square and multiply it by temperature and you will get the so this is at of course this thing, and these are to be computed at t equal to Tc. But however, we want to get it from the BCS theory. Let us see how to get that. So, specific heat discontinuity from BCS theory. Okay, so once again, just to remind ourselves that the quasi-particle energies are given by a xi k square plus a delta t square. And so, this is there, and of course, we have the quasi-particle distribution function is given by the Fermi distribution function, which tells that this is like exponential beta E k plus 1. We will call this as just f k. Now, to remind ourselves, the entropy expression in in terms of these probabilities or occupation or the distribution functions is given by, so entropy is equal to minus k Boltzmann constant, and this is equal to pi log pi. This formula you will see in your first course of thermodynamics, where pi is the, so pi is the probability of a microstate being occupied. Okay. So, in this particular case, so we are talking about the electronic contribution. So, just to make sure that we write it E, and corresponding to the superconducting state we will call it SES, which is equal to a minus 2 k there is a sum over k, and there is a 1 minus f k log of 1 minus f k, and plus f k log of f k. So, that is the form for the entropy, where f k's are the distribution functions, and we have talked about these 1 minus f k's as the probability that these the k states are not occupied, and f k's are the probabilities that these k states are occupied. So, we have summed over them, and so that is the expression. And so, now we can define the specific heat CES, which is equal to TdSES and dt. Now, this is can be written as minus beta dSES d beta, and the reason being that will just give you a derivation of each one of these steps. Let me first write down the steps, and then that will be easier for you to get a feel. So, we will call this equation as equation 1, and we will give a derivation for this. And then there is a CES can be written as 2 beta from here, from equation 1. It can be these are all the same equations, we are just simplifying a step one step after another, but since we have to give a derivation for each one of them, so we are naming them as different equations. And so, this is equal to a delta f k del beta log of f k divided by 1 minus f k, call it as equation 2, and this is equal to nothing but 2 beta square k sum over k and E k and del f k del beta, and so call this as equation 3. Let us write it here. So, CES is equal to so that is minus 2 beta square k sum over k, and this there is a del f k del beta E k, and this is equal to a E k plus beta dEk. Let me write it cleanly. So, there is a beta dEk d beta, and call this as equation 4, and then finally, we will have another equation which is CES, which is equal to a minus 2 beta k, and there is a sum over k, and there is a dFk or del fk, it does not matter, del fk del Ek, and Ek square plus half beta d delta square d beta, and so on. So, this is equation 5. So, finally, we have got this equation for which is the expression for the specific heat due to electrons for the superconducting state. Of course, these are very involved expressions, and we need to derive them, and it will not take much effort to derive them. We will simply have to do it methodically. So, let me derive equation number 1. So, CES is equal to T dSES dt, which is equal to T dSES beta d beta dt. I can write that as a chain rule, which all of you know, where so we are writing it as full differentials, and since beta equal to 1 over kt, d beta dt is nothing but minus 1 over kt square, Okay, so that gives me this is equal to, and then 1 t will cancel and will be left with a minus 1 over k t, which can be written as minus beta d s E s d beta. So, that is equation number 1, which is what we have seen. Okay. Now, for equation number 2, you remember that we have S E s is equal to minus 2 k and there is a sum over k 1 minus f k. These derivations are important, and for you to learn them is also important. That is why I am doing it each step 1 minus f k and plus f k log of f k. So, d s E s d beta is minus 2 k p beta sum over k minus log of 1 minus f k, and so this is equal to and then d f k d beta and plus 1 minus f k divided by 1 minus f k and then a minus d f k d beta. Please do them carefully and not making mistakes, because this, if you make a mistake, then and plus d f k d beta, which ln f k, and plus f k over f k d f k d beta. Okay. So, that sort of it is going to cancel things, minus 2 k b beta sum over k and d f k d beta and log of 1 minus f k minus 1 plus log of f k minus plus 1. So, this 1 will cancel and we can write this as 2 beta k b sum over k d f k d beta, and these two logs can be combined, writing it as f k divided by 1 minus f k. And if you see that, this is equation number 2. This is equation number 2. Okay. So, that is the same equation that we have derived. Okay. So, this is equation 1 and this is equation 2. Let us look at the other things as well. So, now you have f k 1 minus f k is equal to nothing but exponential minus beta e k log of exponential minus beta e k, it is equal to minus beta e k, and so this is of course equation number 3. And equation number 4 is we need to derive it with, then it is a d f k d beta can be written as d f and there is a d of beta e k, and then it is a d e k d beta. If you take beta e k is equal to x, then d f k d beta or del f k del beta does not matter. So, this is equal to d f dx and d x d beta, which is equal to d f d of beta e k and e k. We are trying to sort of do a derivation backward. And so, this is equal to minus 2 beta square k and sum over k, that is equal to, so e k and del f k del beta e k. So, this is an e k plus a beta d e k d beta. So, that is equation number 4, and so this is equation number 4, and we know that your df dx is equal to df dy and dy dx. So, if you take your x equal to beta e k and your y equal to e k, then your df k d beta e k equal to df k d e k and d e k d beta e k, it is equal to 1 over beta df k d e k. So, so that is there, and then of course, your beta e k d e k d beta, this is equal to beta by 2 e k d delta square by d beta, and your well, this is d beta, and because your e k is equal to delta square by psi k square. Okay. So, basically this is all. So, this is equation number 5, and this is what we have derived. If you look at it here, this is that equation that we have derived. Now, what is the meaning of this equation, and what it really tells us is that the first term is due to the usual quasi-particle contribution to the specific heat of electrons. Okay. The second term is important. Term would not have been there if there is no gap, or the gap does not depend upon temperature. This comes because the gap has a dependence on temperature. So, that is why the specific heat now derives a contribution from two terms. One is the usual from the quasi particles, the other from the temperature dependence of the specific heat, the gap. So, as so basically just we are almost completion towards nearing completion for the calculation of the specific heat discontinuity. So, at T much smaller than Tc, your CES is exponentially small. It goes as Tc exponential minus Tc over T, where Tc is much smaller than T is much smaller than Tc. Okay. So, near Tc, delta of T goes to 0. So, we can replace E k by xi k. Okay. So, the first term in the expression of the specific heat, which we told about the quasi particle, the first term that boils down to CES. The second term of course is equal to 0. So, this is equal to, it is not the second term of course has a value, and this is equal to a 2 pi square by 3 NEF and a k square T. Okay. So, that is a linear contribution to the specific heat, which we are very well exposed to in the context of the metallic specific heat. Now, the second term, that is the d delta square d beta, which is this term, the second term in equation 5 is d delta square d beta is actually finite, below Tc, and in fact, it is basically it is large, not only finite, it is large because the variation of delta with respect to temperature is very sharp there, but this is equal to 0 above Tc when delta completely vanishes altogether. So, now this gives rise to discontinuity. So, this term gives rise to a discontinuity because this is finite just below Tc and it is 0 just above Tc. So, delta C, which is equal to CES minus CEN, which is at T equal to Tc, it is equal to n epsilon f k b beta square d delta square d beta and minus infinity to plus infinity d f d xi, this xi has to be in mod. Now, of course, this is equal to n epsilon f and minus d delta square d t at t equal to T c. Now, basically where we have used that df d xi is same as df d xi, which is an even function. So, now if you use this formula that we have said, that delta t is equal to 1.74 delta 0 1 minus t by T c whole to the power half, and calculate this d delta square dt, evaluate it at t equal to T c, then these delta c can be computed, which comes out as 9.4 n epsilon f and a k t square T c. So, that is the value of the discontinuity. So, this is the magnitude of the discontinuity, where of course, your delta 0 as told earlier during the discussion, it is equal to k T c. So, the normalized discontinuity, if you are interested in that, that is the discontinuity divided by the value of the metallic specific heat, which is a well known quantity. So, this is equal to that 2 pi square over 3 value, which is what we have just seen here, this 2 pi square by 3, and this becomes equal to 9.4 divided by 2 pi square by 3, and this is equal to 1.43. So, this is the value, or rather the important result that is important in the context of experiments, that is measurable, that this is the jump in the specific heat. And what happens is that if you plot the specific heat and as a function of t, it, as I told earlier, that it grows like this, it drops like this, there is a vertical drop, I am so sorry, this has to be shown, and then of course, it goes like this. Okay. So, this is at T c, okay. And there is this discontinuity here is the delta c, and if you want this discontinuity to be to be divided by the CEN, which has a value, whereas the normal specific heat goes like this, the dashed line, and then it so the normal state specific heat goes like this. So, basically this is a hallmark signature of a second order phase transition. So, basically you see that there is that these two values just below T c and maybe just above T c, you give the you increase the temperature, but the specific heat acquires the same value, and this is the fact that the latent heat of course is not there, and it is a feature of a second order phase transition. So, we have comprehensively given an account of what would be the experimental verification of superconductivity, that is how superconductivity would be realized. And of course, there are many other things like a field cooled and a zero field cooled protocol that we have given earlier. But importantly, the Meissner effect, which is basically the diamagnetism and the specific discontinuity, along with a sharp drop of the resistivity below T c, are what characterize superconductivity.